Still in chapter 21.2.
Are you recording?
I am. Not a lot of notes. And it's on electric potential. We've talked about one type of potential so far. Guys, you're being rude. We've talked about one type of potential so far. That was what kind?
No, the gravitational.
Yeah, we talked about elastic and gravitational, so there's been two times. But that gravitational, and so electric potential is going to be very similar to gravitational, okay? With a few little kinks, like you know how that goes. Can't make it too simple. Okay, I'm actually going to reorder things just a. Nope, can't. So we're gonna. No wait. I'm trying to decide how I might want to reorder this. I'll just follow the order I have. Okay, so let's say I have two long parallel plates. And I'll take the parallel plates and I'm going to charge them oppositely. Okay, so one will be positive and one will be negative. Let's take a second and examine the electric field that we're going to see between those two plates. Okay, what we're going to see is two interesting properties. First of all, the electric field between the two plates is going to be linear. Okay, there's not going to be any curves. Okay, which way should it be pointing? Up or down? Down. Okay, so the electric field here is going to be straight and pointing down. The second thing that we're going to observe deals with the strength of an electric field. If I just have a charged particle, so like a positively charged particle, as I get farther away from the charged particle, what happens to the electric field? It gets weaker. Okay, what we're going to see between two charged plates, guys, two parallel charged plates, is there's no difference between the electric field here and here. Okay, so and I'm going to explain that in just a second why. So with two parallel charged plates, we have a linear. Well, what's the word? Well, I'm trying to think. What a linear means straight, and then it's the same electric field. Linear,
Parallel.
constant. I even had that on my paper. Okay, and the reason why we have this constant electric field deals with the fact that we have two charges. So let's say I have a charge right here. We'll make it a positive charge. It doesn't matter though. Okay, if it's a positive charge, then there should be two forces on it. There's the force from the positive plate pushing it down. Okay, so there'd be a certain amount of force there, and then there'd be the force from the negative plate also pushing it down. And since it's closer to the negative plate, what we would see is that force would be much larger. Okay, so I'd have kind of a small force from the positive plate, a big force from the negative plate. Let's say I took this particle and moved it up. Move it over here. What we're going to see, guys, is as it moves away from the negative plate, the force from the negative plate is going to diminish. But as it moves toward the positive plate, the force from the positive plate is going to increase. So you see how as you're moving from one to the other, the forces are kind of doing the opposite. Okay, so what that ends up with, guys, is a constant electric field throughout the charged plate. Okay, we have an equation for that electric field, but frankly, I don't care. Okay, so that's one of the things that we're skipping. Okay, and it's just not interesting. Okay. So we're just gonna skip that, and so it's gonna seem like we're jumping because we are jumping. We're skipping topics. Okay. So this brings us to electric potential. Well, it doesn't bring us to electric potential. We're jumping to electric potential. We are going to relate back. Let's say I have a positive charge, and I have another positive charge. What do those want to do?
Repel.
They want to repel. If I take this charge and I move it in, it's going to want to repel even more, right? Okay, so what I would say, guys, is as I take these like charges and move them together, I would say that the electric potential is increasing. Let's say I have a negative charge and a positive charge. They want to move together. If I take this and move it away, then, there's more potential energy being built up because there's more room for it to move together now. Okay, so when like charges move together, the electric potential increases. When opposite charges move apart, the electric potential increases.
Would there be a distance at which the opposite charges would lose the potential energy?
Yes, in the same way with gravity. Okay, we calculated that, and I don't remember what we calculated. It ended up, was it twice the...
Did you say they were both an increase?
Both of these I've drawn are an increase. Okay, so the electric potential, exactly the same idea as the gravitational potential. Okay, the gravitational potential was related to the amount of work that gravity could do on the object, and it turned into kinetic energy, right? Okay, same thing here. My electric potential is going to be related to the amount of work a charge can do. Okay, if I take the positive and negative and separate them more, it can do more work because it has more distance. Remember, work is force times distance. Okay, if I take the two positives and I push them together, then there's more force. So that in that case, the force increased. Okay, so that can do more work. Okay, so my electric potential related to the amount of work a charge can do. My electric potential, guys, is going to be measured in volts. Probably heard that before, right? Okay, and 1 volt is 1 joule per coulomb. Okay, 1 volt is 1 joule per coulomb. Okay, so if I have 1 volt of electric potential built up, then 1 coulomb of charge could do 1 joule of work. Of work. Make sense?
Yes.
Okay, so if I have a 6-volt battery, okay, that big battery I have, 6 volts, okay, that's how much voltage has been built up. Then 1 coulomb of charge would do a joule of work. Okay, I'm gonna have to do some research on that. Some research, because that seems, what I'm saying there just doesn't seem right. Okay, because a coulomb of charge is very big. I don't think that a battery even has a coulomb of charge, and it can do more than 6 joules of work. I'm gonna have to get back to y'all on that. Anyway, okay, so back to my charge plates, guys. For charge plates, the voltage across the plates is going to be equal to the electric field between the plates times the distance between the plates. Okay, and this does go on your equation sheet. And for the used for, we'll put electric potential between parallel plates. Electric potential between parallel plates.
So is there electric potential between perpendicular plates?
No.
Is there an equation for the electrical potential between perpendicular plates?
I don't know how you would have, what do you mean perpendicular?
Like, say a plate right here. Is there an equation for that? Like up down.
No.
And that would probably be That's on parallel.
No.
Questions.
That yeah, I've never heard anybody using perpendicular plates. Okay. So far, so good. All right. So the voltage, guys, is going to be if I know the voltage across two things, okay, then that tells me a lot. And by the way, guys, the reasons we're using delta V there is because you always measure change in potential. Okay, there's no absolute potential. In the same way that there's no absolute gravitational potential energy. I mean, if I took something and picked it up from the table up to here, there's no absolute gravitational potential. That's my delta GPE, right? Okay, so same thing with here. Okay, there's a delta V. So the voltage is going to tell me, guys, how much. All right, it takes a certain amount of voltage to make electricity work, okay, or to make charge flow. What we saw up here, guys, is when I was using the Van de Graaff generator, okay, when I had it really far away, okay, we saw not much, no sparks, right? However, when I pull it closer, we do see a spark there, okay, and that's dependent on the voltage, okay. And so the rule that kind of tells you how much voltage you need to make the spark work is called the dielectric constant. Yeah. Okay, and the dielectric constant, guys, is related to the voltage required to cause an insulator to break down. I know what they're talking about too. That's human anatomy and physiology, and they've gotten to a certain section.
What section was it?
Yeah. All right, to break down into a conductor.
Yeah.
Okay, so for air, in order for air to conduct that electricity and for us to see a spark, air has to break down, okay, and become a conductor. Okay, and that is measured by the dielectric constant. For air, the dielectric constant is 3 megavolts per meter. Okay, so for every meter of air, you need 3 million volts of electricity to break down the air.
So much.
To cause the air to conduct electricity. Okay, so, huh?
What do you mean by breakdown?
It causes the air to become ionized and turn into a plasma, and plasma will conduct. So a thunderstorm, if I'm talking about from the cloud to the ground, and that could be 2,000 meters. Okay, so if we're talking 2,000 meters, then I have 2,000 times 3 million. Okay, that'd be the amount of voltage between the ground and the top of the thunderstorm. For water,
What voltage kills
it takes more than just voltage. This is 200,000 volts. 200,000 volts is way more than enough to kill a person, but it has very, very low current. Okay, and so it takes, yeah, it takes a combination of both. Okay, you got to have a lot of current and a lot of volt. But actually, a very, very low amount of current will be deadly. But we'll talk about that later. For water, guys, it's 81 volts per meter. Okay, the wall, guys, is 120 volts. Okay, so that's the reason why if your hair dryer drops into the water, okay, and you're in the bath, you're getting shocked because 81 volts per meter is lower than 120 volts. Okay, but that's why I can stick my finger in that water with the battery because that water with the battery is only 6 volts. Okay, so it doesn't surpass the dielectric constant. It doesn't break down. What now?
If that battery is plugged into a wall, and then put it in the water, then it
if the wall was plugged into the, I would not. Well, first of all, actually, if it was plugged directly into the wall and you went into the water, then the breaker would turn off and it would just shut off.
Oh, okay.
Okay. So that's the reason. Typically, if you're in the bathtub, I mean, you're not just going to sit there for like 3 hours getting electrocuted. I mean, it would shut off very quickly. Okay. So let's do a little example of this. How strong should an electric field be between a cloud and the ground?
Are we gonna write the question?
Well, you don't have to write. I mean, it's your notes. To cause lightning if the cloud is 2,000 meters high. Okay, so how strong of an electric field should be between a cloud and the ground to cause lightning if the cloud is 2,000 meters high? Do y'all see a similarity here between lightning and this?
Yes.
I mean, it's reversed, but in the cloud, pretty much a flat surface negative, in the ground, pretty much flat surface positive. I mean, if we zoom back a lot, that's pretty much what we have. Okay, so we're going to use parallel plates to represent the cloud and the ground. Okay, so my distance between the parallel plates is going to be 2,000 meters. Okay, the dielectric constant is 3 million volts per meter, and so therefore the voltage required, is going to be 3 times 10 to the 6 volts per meter times 2,000 meters. Okay, so that's going to be 6 times 10 to the 9th volts. And we're looking for the strength of the electric field. Alright, so the electric field, guys, is equal to, the voltage difference is equal to the electric field times the distance between the plates. So if I want the electric field, I divide by the distance. Do y'all see where this is going?
Yes, we do.
So the electric field, guys, is going to be equal to 3 times 10 to the 6th meter. Newtons per coulomb is the unit. So the electric field required for any distance through the air is 3 times 10 to the 6 newtons per coulomb. Okay, so when I'm zapping between the orb and the Van de Graaff generator, that's the same amount. That's the same strength of electric field as a lightning strike. Same strength of electric field. However, what we're seeing is it's nowhere near as much voltage because the distance is much smaller. Making sense? Okay, so far what we've been talking about is just flat plate, flat plate. But let's say we have one plate that's not flat. So we'll go with the top plate being flat. Let's take the bottom plate and let's curve it. And we'll put positive down here. And we'll put negative up here. Do y'all agree, since they're negative up here, that the positives are going to tend to accumulate in the orb? Okay, the positives will tend to accumulate in the orb. So when we go to draw out the electric field, guys, the electric field here should be facing which direction? Upward. Okay. what we're going to see, guys, is that electric field is going to tend to be concentrated on the top of this thing. So in other words, guys, the electric field is stronger on a curved object. Okay, so electric fields are stronger on curved objects. Give me a second, I'll tell you why. It'd be the opposite. It'd be weaker. So I guess I should say curved up. Alright, and this, because it's closer, so I get, well, it's not only is it closer, but I get an accumulation of charge. Okay, the charge density on that is stronger than the charge density here. And the smaller that distance, guys, the pointier it gets. Okay, then the stronger and stronger and stronger the effect is. Okay, so that leads to something called coronal discharge. And coronal discharge, guys, is a discharge of built-up static charge without it being like lightning. Okay, I'm going to show you a picture of that, and then I'm actually show you a real person too. It is a buildup of, I mean, it's a release of static charge. And this right here is coronal discharge. Okay, notice, guys, that what we're seeing is a kind of like a mass exodus of charge. Okay, it's not like one little, okay, it's not like a path. Okay, what I'm seeing is charge, lots of charge being released. Okay, so coronal discharge. So if I take this object and I get it up close, okay, and it starts doing the little zapping thing, okay, but then that's one effect of charge being built up. However, I can take that. Let's say that's the top of the. Let's say that's the top of the orb, and let's say I take a little point here. Okay, that's going to take, and it's going to make a very strong electric field at this point right here. Okay, so what we'll see is a lot of coronal discharge from that point. Okay, so if there's a lot of coronal discharge from that point, that means that the charge is no longer being built up on the top of that. Okay, so I shouldn't see any zapping between the two objects if I take that point and put it on there. Okay, so let me show you that.
Wouldn't you see it if it was near the point?
Why not?
Wouldn't you see
No.
zapping? Why not?
Okay. Okay. I will in a second, but we
You can see it reflecting.
but maybe I should turn the lights off. I don't want to ruin my. Okay, so anyway, we see that discharge and charge there.
I knew you'd get it.
Okay, however, guys, I'm gonna put a little a staple on there. Okay, so now I have a little point. Okay.
Wait, why isn't it causing a
Just
so
wait.
little?
Just wait for the mass exodus.
Guys, so why isn't it? Why am I not seeing anything? I mean, look how close it is. Why am I not seeing anything?
Because it has all of this stuff.
Because guys,
Charging off of the
all the charge. If this point has a ton of electric field on it, so all the charge that's being built up is just being sucked right out into the atmosphere. Okay, when that point's not there, then we're not seeing that. Okay,
So is it exiting to the point?
it's exiting through the point, and remember that picture?
Yeah.
Okay, that's what's happening. It's exiting through the point, and so remember, it takes a certain amount of charge build up to make that zap happen. Well, if enough charge doesn't build up, then the zap doesn't happen.
Interesting.
How can the charge leave that little point fast enough to not build up the zap?
The smaller the point, the stronger the electric field. And so it leaves this little point faster than it does this whole orb.
That doesn't make any sense. Should it leave faster from the bigger area because there's more area to leave?
You remember that video when the guy had the needle and he couldn't get it to jock and he was charging it? It's kind of the same.
I know
Mhm.
that. I mean, like, you would think.
All right, so
I know.
this kind of takes us back to the video, guys. I have a house, and it has a lightning rod next to the house. What is the purpose of the lightning rod? To attract the lightning, or to make the lightning not come to the house? To make the lightning not come to the house.
By attracting it to itself.
Okay, but essentially what it does is there's a whole bunch of positive charge down here. It dissipates that positive charge through coronal discharge, and so the lightning's not attracted to it because it's not positive, huh? When if it does hit it, it would route it down. However, guys, lightning rods don't really work. Okay, and here's the reason why lightning rods don't really work. Here, the reason why that's effective is because the coronal discharge of that point is higher than the amount of charge being built up by the Van de Graaff generator. Do you think a lightning rod is ever going to be capable of discharging enough charge to outdo a thundercloud? I mean, a thundercloud builds up builds up charge way faster than a lightning rod could ever hope to dissipate charge. Okay, so lightning rods are ineffective, pretty much. And you ever heard the old thing? Oh, you shouldn't have a metal umbrella out in a thunderstorm because it'll attract lightning. Well, technically, a metal umbrella should do the opposite of attracting lightning because it has a point. Okay, so it should be it should be dissipating charge. Okay.
Well, they said never to do that. Like, you're not supposed to walk with metal walkers.
Absolutely fine. Here's my suggestion the old suggestion is don't walk with metal objects out in thunderstorms. My suggestion is don't walk out in thunderstorms. You know.
But you said that golfers, whenever they like swing their feet up,
I didn't say that.
I don't remember.
but they like
They said that on the
chill whenever
movie.
they.
It's because they're the highest point.
Oh, not because it's metal.
Oh, so if it hits someone like really low to the ground, you should be alright. Stab them twice.
And that's a myth too. I don't know why he said that.
Well, all I know is
My understanding, okay, lightning travels in like 50-meter segments, and so, I mean, 50 meters is very high. So I mean, it's like 50 meters up, and so it can't detect. I mean, it can't really detect what's on the ground at that point, and so it travels. I mean, it's not. My understanding is there's very, very little effect of height changes and that kind of stuff. Well, no.
Is it attracted to water? Because you're not supposed to be in a pool.
You're not supposed to be in a pool because if lightning strikes water, it can travel a pretty good distance.
Not because it's attracted to water.
Yeah, lightning is deadly a longer distance in water than it is in dirt. Plus the fact that if you're in a pool, then you're out in a lightning storm. You shouldn't be out in a lightning storm.
Oh, when lightning strikes.